I'm so happy that Dr. Blakeslee is here. We're going to really enjoy it.
Thank you. Lovely. Thank you very much, everyone, for coming. It's a great honor to be here at the Molokai Public Library to talk about our place in the cosmos. So I won't really give any background about myself, just to say that, yeah, my position is called Chief Scientist at Gemini Observatory. Gemini means twins. There are twin telescopes. Actually, yeah, office. If we just leave it office, would be great. Yeah, because I have some images. So we have twin telescopes, one in Hawaii on the Big Island, and one in Chile. And they're identical telescopes. They study the sky from both hemispheres. That's one of the power of the Gemini Observatory, because you can only see half the sky from any one location, from any one hemisphere. So by having two, one in the northern hemisphere and one in the southern hemisphere, we can see the whole sky. Okay, so talking about our place in the cosmos. So our place in the cosmos right now is at the Molokai Public Library. As I said, I'm really honored to be here. You have all these beautiful books here, the summer reading program we just heard about. This is one of my very favorite books, The Brothers Karamazov by Fyodor Dostoevsky. You probably see some people have read it. Perhaps maybe the greatest novel ever written. And quite inspirational. If you've never read it, I highly recommend it. And it's been said that Brothers Karamazov contains all there is to know about life, but it's still not enough to get you through life. So we have to kind of go through together, making up as we go. In the Brothers Karamazov, it's many different themes, many different subjects, many different ideas, and many different characters, more characters than you could possibly keep track of. And one of the characters towards the end has a dream, and he's visited by the devil in the dream. And the devil tells to this character, one of the brothers Karamazov, he says, "Once there was on your earth a thinker and a philosopher who rejected everything, laws, conscience, religion, and above all, an afterlife. So when he died, he expected to plunge into darkness and nothingness, but instead he found before him an afterlife. Surprised and indignant, he said, 'This is against my principles.' And for that, he was punished. He was sentenced to walk a quadrillion kilometers through the darkness, where we have the metric system in the afterlife now. And when he has finished walking that quadrillion, the gates of heaven will be open to him, and he will be forgiven." So that was really interesting, a quadrillion kilometers. When you talk about numbers this big, a kilometer is pretty much the same as a mile. So a quadrillion kilometers, a quadrillion miles, it's pretty much the same. And these are actually the kinds of distances that we use in astronomy to describe the universe. So who knows what a light year is, to measure the distance in the cosmos? Is that people? Yeah. So people are familiar with that. It's the distance that light, which travels at 186,000 miles a second, could travel in 1 year. And in 1 year, anybody know how many seconds are in 1 year? It's about 31 million seconds in a year. So 31 million times 186,000 would be the distance of a light year. It turns out to be about 10 trillion kilometers, or 6 trillion miles. And a trillion, so we have 1,000, which is 1 with 3 zeros after it. We have a million, 1 with 6 zeros, a billion, a trillion, a quadrillion. Every time you just multiply by 1,000, so you add 3 more zeros. So a quadrillion is 1 with 15 zeros. So this 10 to the 15 is just scientific notation for 1 with 15 zeros. And a light year is 1 with 13 zeros. And so the difference between 13 for a light year and 15 for a quadrillion kilometers is just 2, right? 13 to 15, or 1 with 2 zeros is 100. So a quadrillion kilometers, which this philosopher was sentenced to walk, is equal to 100 light years. So he was sentenced for his punishment to walk 100 light years. So if he could travel at the speed of light, he'd be done in just 100 years. So very simple. However, We walk much more slowly than that. The typical pace might be 5 kilometers an hour. That's 3.1 miles an hour. That's a respectable, comfortable pace, not too slow. And walking at that speed, it would take him 23 billion years. So that's actually quite a bit older, quite a bit longer than the entire age of the universe, which we think is about 13.5 billion years. So at the end of those 23 billion years, when he is forgiven and able to enter the gates of heaven, he will have walked 100 light years. So how far would he have gotten? Would he still be in our solar system? Would he be beyond our galaxy? It's actually an interesting question. So we know we live on the planet Earth. We live here on Molokai, in the Hawaiian Islands, on the Pacific Ocean, on the planet Earth, which is one of 8 major planets now that Pluto has been reclassified. One of 8 major planets and half a dozen dwarf planets and lots of other stuff, comets and asteroids going around our sun. Our sun is one in 10 to the 11, which is 1 with 11 zeros, or 100 billion stars that orbit about the center of our galaxy, the Milky Way Galaxy. And our Milky Way looks something like this, a nice spiral. Maybe it has a little bit bigger bulge. Of course, we can't take a picture of the Milky Way because we're embedded within it. We can't get up above it and take a picture. So the sun is one of 100 billion stars in the Milky Way. The Milky Way is one of about 40 or 50 galaxies in a little group of galaxies, which is called the local group. That's what the Milky Way lives in. And then that local group is part of a larger structure that we call the Virgo supercluster, which has something like 60,000 galaxies in different groups and clusters. And it's typical of the large-scale structures in our universe. And our universe is about 13.8 billion light years across. It's the distance that light has been able to travel in the history of the universe. And I'll talk at the end how we know the age of the universe, and the age gives us the size. Okay, and so just coming back to our galaxy here, our Milky Way Galaxy, about this size, is something like 100,000 light years across. Okay, so this philosopher was sentenced to walk for 100 light years. And the galaxy is 100,000 light years. So in his journey for those 23 billion years, he will travel far beyond our solar system, because our solar system is only like a light day, less than 1 light day in size. But he will travel 100 light years, which is only 1,000th of the distance of our galaxy. So he will still be in the sun's neighborhood, the local neighborhood, where we are today during that journey of 23 billion years. So, okay, so let's go back to our home, this Earth, our place in the universe. This beautiful oasis of life in this vast cosmos. We are able to live on this Earth because of the stuff you see here. Of course, the water, the liquid water that we need to drink, but the clouds. And the clouds live in our atmosphere, this protective layer that allows us to live and move and have our being and breathe. And the atmosphere is a wonderful thing. We couldn't exist without it, as I said. It's the stuff that we are made of. But it does cause problems for people like me, for astronomers, because this protective atmosphere is kind of really like this murky, bubbly soup surrounding the Earth. And as these beautiful parallel light rays come from the sun, come from stars, like rippling out in every direction from every point source, from every source of light in the universe, they hit our upper atmosphere, and they get all messed up, right? So you can see it. It's just like a light beam going into a pool of water. It refracts, it bends, because the index of refraction changes. And so the same thing happens with our atmosphere, but it's worse because it's not a completely smooth and stable atmosphere. It's ripply and bubbly and very turbulent. The turbulence, like when you're flying in an airplane and everything starts shaking and you start praying, that stuff messes up the light that we're trying to study from beyond our atmosphere. And so there are some ways, and it's wonderful to see the twinkling stars and things like that, which is the effect of this. But if you want to study things with very high precision, very high spatial resolution, you have to solve this problem some way. The Hubble Space Telescope does it in one way, in one sense, a very easy way. It's in orbit above our atmosphere, so it's unaffected by the blurring effects of our atmosphere. But it's also a multi-billion-dollar observatory satellite. We only have one of them right now. It's been in operation since 1993. Probably pretty soon to die. It will be replaced to some degree by something that'll be launched, hopefully in a couple of years. But it's not this a perfect solution because it's so expensive to launch things into space and to maintain them. And now it's pretty much, without the space shuttle, it's impossible to actually service it. There were a number of servicing missions to repair it during the course of its 25 years, but that's no longer possible because we no longer have the space shuttle. And so we need a different solution. And what we use at Gemini Observatory, other observatories in the world, other large observatories, is something called adaptive optics. And it works with lasers. So here we are in the dome of the observatory. This is actually at Gemini South. Beneath the telescope, you see the slit of the dome is open. And the light, of course, comes through the slit, hits this mirror down here, gets reflected up to a tiny secondary mirror there, and then through the hole in the primary, the big mirror, to the instruments. And if we don't correct for that atmospheric turbulence, that blurring effect, our images are not great. And so we want to correct for that. And one way to do that, or actually the way to do that, is using lasers. So we launched a single laser split into 5 different spots. It's kind of technical, you can ask me about it later, but it makes a tiny little constellation high in the atmosphere at a height of about 90 kilometers or 55 miles. At that height, there's a thin layer of sodium atoms, which kind of grows by the debris from meteorites that impact our atmosphere. And so there's a thin layer just because of the density and the mass of sodium atoms. They like to live at this height of 90 kilometers. And so if you shoot a sodium vapor laser high into the atmosphere, it will excite those atoms at that height. And so you know exactly how high it's going, 90 kilometers. You can take an image of this little constellation, and since you know everything about that constellation, you know how much energy you put into it, you know where those little stars exactly should be because you've designed the experiment. You can monitor how those little stars move and jiggle and change size. And there's something called deformable mirrors or adaptive mirrors they're like a mirror, but they're kind of rubbery. So they have all these actuators in the back, hundreds of actuators, and they sense the motion and they just move 200 times a second, 300 times to compensate for the jiggling that results from the atmosphere. So that's called adaptive optics. And by measuring the jiggling of these little artificial stars, these laser point sources, you can correct for the atmospheric turbulence even down here beneath this soupy atmosphere that we live in. So it's a different solution than is made by the Hubble Space Telescope. It's still not cheap, $10 million to make a system like this, but compared to 10 billion, it's a bargain. Right? And so let me just show you. So this is Gemini South. This is just one night of operations with our laser. This right here is one of the Magellanic Clouds. Has anybody heard of the Magellanic Clouds? Yeah, the Milky Way has several satellite galaxies. The 2 biggest are called the Large and Small Magellanic Clouds. They're something like 50,000, about 150,000 light years, so quite close in cosmic terms. And so they're easily visible to the naked eye. They're called the Magellanic Clouds because the first European to notice them was Ferdinand Magellan, when he circumnavigated the world and went far south of the equator. Anyway, so this is one night of operations at Gemini South compressed into 1 minute. And so we track, the telescope is studying different objects in the night sky, and so it's moving and tracking. This is the moon. So we're able to study certain kinds of objects when the moon is out, and you can see the moon setting. The telescope pointing in different directions, shooting its laser. Again, this is sped up by, you know, factors of 50 or something. There you see the moon setting. So we were able to operate pretty much all night, studying different objects, as long as conditions are good and clear, like it is on this night. Now we see the moon setting over the Pacific, the South Pacific there, and then suddenly it becomes much darker. And so now you see the large and small Magellanic Cloud. So this was a very, and you see some meteorites flying by. That low one was a plane. And then you see, yeah, sunrise. So that's a complete night of operation at Gemini South with this laser that allows us to correct for this the turbulence that we have as a result of our atmosphere. But even though the atmosphere seems very substantial to us and you know, causes all these storms and sometimes it seems oppressively hot or incredibly cold, and if you're from the mainland, sometimes enormous quantities of snow fall through our atmosphere as a result of condensation. And it causes all sorts of problems for astronomers trying to study things, and we have these different solutions. But one thing I want to emphasize that our atmosphere is actually very thin compared to the size of the Earth. You know, just 5 miles up, you need oxygen. It's that thin compared to like 8,000 mile diameter of the Earth. So it's just a tiny thin layer on top of this big globe. So it's thin and it's fragile. And not only is our atmosphere very thin and small compared to the size of our planet, but our planet is incredibly tiny compared to something like a star. This is a true scale perspective of our sun, taken the image in H-alpha lights, which shows certain types of emissions, compared to our Earth right here, the tiny little ball. So this thing right here is called a solar prominence. The sun goes through a cycle, a 22-year cycle actually, of kind of active and inactive. And over the course of that 22-year cycle, its activity changes a lot. So sunspots, prominences, essentially explosions, magnetically induced explosions. So this is much larger than the size of our Earth. And sometimes these things can just break away from the surface of this sun and cause enormous quantities of solar particles to flood in our direction. There's always this solar wind. And the solar wind is not the radiation, the light that heats us and that we see, but it's these charged particles that stream off because of the very strong magnetic fields. And the worst of these, so when there's a particularly large, something like this, storm on the sun and it breaks away, it can stream out in any direction. If it impacts the Earth, that can cause some problems. So the worst ever recorded was in 1845. It's called the Carrington Event. It was actually witnessed by an amateur astronomer, and it took down all these the very early telegraph lines. So throughout the United States, throughout Europe, that had been set up. They fried, like the stories of the little paper from the telegraph lines is setting on fire because of this explosion of charged particles traveling towards us. These things, we don't really know how rare they are because the time scales are long, and we've only been studying it for a couple hundred years. But this is the kind of event that could wipe out the entire power grid. So when that Carrington event happened in 1845, one benefit were the beautiful aurora displays, which are normally confined to the poles. They reached as far down as the equator, Hawaii. You can see the aurora borealis and the aurora australis. There was actually a similarly large one in 2012, coincidentally, but it missed the Earth, right? So again, these things kind of stream out in a certain direction, and we were safe, but you know, it's something to keep in mind. So if you want to print out your important electronic events. So this is just an illustration of what I was saying. So here's the sun. This is not to scale. So the Earth is actually much smaller and much farther away. But the sun is constantly sending out these charged particles, the solar winds. And what protects the Earth is, in this case, not the atmosphere, which protects us from UV. The ozone protects us from UV from the sun, but our magnetic field. the Earth has a magnetic field which has guided sailors on the seas for centuries. But the other thing that it does is it protects us from the worst of the high energy particles that are constantly barraging us from the sun. And they can stream along, and some of them can get down into the north and south poles because they can follow these magnetic field lines. And that's the reason why we have the Aurora Borealis and Aurora Australis, particularly, especially near the poles, because these charged particles can reach the tops of the Earth's atmosphere. If an enormous explosion can just really compress these lines and just stream right through them. But those, fortunately, are rare. So that's what protects life on Earth, in addition to the ozone, the Earth's magnetic field. For instance, in comparison, this is a 2-scale comparison of, so what's this planet, you guys?
The moon.
No, yes?
Mars.
Mars, that's right. So this is Earth, and the next planet out is Mars. Mars is not that much further away from the sun than the Earth is. As far as we know, there's no life on it, but it has this nice atmosphere. You can see this haze, this beautiful morning haze, kind of right on the edge there. It would be morning if you were standing right here. Has this nice south pole, and in fact, this is summer at the South Pole, so there's even a bigger polar cap on the north. There's these dark areas, it's called Syrtis Major, different landscapes. 100 years ago, astronomers thought this might have been vegetation and seasonal changes. Maybe in the past, well, we think in the past that there was liquid on the surface of Mars when it had a more substantial atmosphere. There is not, as far as we know now, perhaps beneath the surface, there's some permafrost. But the other problem for life on Mars is that it doesn't have a magnetic field. Because it's so much smaller, it cooled a lot faster. So it no longer has a liquid iron core. And in order to have a magnetic field, you need a liquid iron core spinning around to create that magnetic field. And so Mars long ago cooled to its core, and so it's solid. It has no magnetic field, and so therefore it has no protection from these solar particles that constantly are impinging upon it. And so any life would be very difficult. It would have to be subsurface to endure that solar winds and solar explosions. On the other hand, okay, so what's this one? Jupiter, yeah, that's right. So Jupiter's much bigger than the Earth. It has an enormous magnetic field, 1,000 times stronger than the Earth's, comparable even to the Sun's. But what it doesn't have is any solid surface at all. So it's just a huge ball of gas. And so if you were to plunge into it, you would hardly even notice as you kind of reach the top of the atmosphere. But as you get deeper and deeper, suddenly it's like diving deep below the surface of the ocean, and just the pressure would increase enormously. It's mostly hydrogen and helium, methane, and then at some point it would just become this crushing pressure. And in fact, we had one satellite mission actually did that experiment that orbited Jupiter for a few years and then plunged into the center until it was crushed by the atmospheric pressure. It has no solid surface, just gas that gets denser and hotter and thicker as you go deeper down.
What
So,
happened?
yeah.
Was it, I can't remember, 20 years ago, the asteroid, what was it, hit Jupiter or
Yeah,
hit the other one?
1994, yeah, so
And it hit,
comet Shoemaker-Levy 9. Yeah, so yeah, it was, I don't have any pictures of that in this talk, but that was an interesting event. In 1993, this comet was discovered, comet Shoemaker-Levy 9, and it was realized that it was actually in orbit around Jupiter, and it was in a decaying orbit, and it was predicted that it would impact Jupiter. And there were all sorts of predictions, what's going to happen. Most people said Jupiter's just going to swallow that thing up and it's going to disappear and nothing will happen. But in fact, it impacted Jupiter with a force of millions of nuclear bombs, right? So it's something like a 10-kilometer size ball of ice and rock. And it created these scars on the surface of Jupiter, these big black blotches, kind of this size.
but I mean, as it went in and broke up, and the planet was going around, revolving, is that it?
The planet, yeah, that's right. So as the comet was coming towards Jupiter, the tidal forces ripped it into something like 28 pieces. each kilometer
I mean,
size.
the asteroid is the size of Earth, right?
No, it's like something like 10, 12 kilometers, so 8 miles. Yeah, and it broke up into smaller pieces. So it would have devastated life on Earth. It's the kind of event that probably wiped out the dinosaurs. But the good thing is that Jupiter protects us. So Jupiter has a magnetic field 100 times bigger than the Earth. And it sits out there beyond the orbit of Mars, just deflecting things out of the inner solar system. So the likelihood of something like a comet or an asteroid impacting Jupiter is 1,000 times higher than Earth. So that's one of the reasons why life has been so resilient on Earth. So, thank you, Jupiter. That's right. The next planet out is this one. We all know this one, Saturn. So this beautiful planet, and unlike the other pictures, this one is not taken from the Earth. And how do we know this? It's not taken from the Earth. That's right, from this direction. It's taken from an extremely successful satellite called the Cassini Mission that was launched, I think, in 2004. Got there something like 2006. It orbited for 11 years, I think, and then finally it plunged into Saturn about a year and a half ago. And it was, so over the course of 10 or 11 years, it took all sorts of beautiful pictures like this. It studied the 60 or so moons that Saturn has. And one particularly striking picture, I think, is this a solar eclipse, essentially, taken from Cassini as it's behind, this Cassini satellite, as it's behind Saturn. So the sun is on the other side. Jupiter is probably way off there in the distance. But all the inner planets, Mercury, Venus, Earth, Mars, of course, are much closer to the sun than Saturn. So those from Saturn, those stay a lot, those always stay near the sun. Okay, so we're looking at Saturn from behind during a solar eclipse. Essentially, the satellites just pass into the shadow of Saturn. And you can see the rings, the incredible structure being lit up by the sun, kind of in silhouette. This outer ring is called the E ring. And it was a mystery for quite a while because it continually is replenished. And now we know that it's because ice geysers from the moon Enceladus, which is kind of in the orbit of this E ring. So it's continually spewing out these icy water particles, in fact, which shows that it has a subsurface ocean, which creates this outer E ring. But the other thing I want to highlight, as I said, all the inner planets would be close to the sun from this perspective. And there we are, there's the Earth. The Earth seen by the Cassini spacecraft. Can anybody see that tiny little dot there? Can you see? Tiny dot. Right there. So that is the Earth seen from the Cassini satellites in eclipse. So as I said, Saturn has something like 60 moons, depending upon how you count them, because some of them are pretty small. And there's no definition of how small something is before you call it a moon. But the biggest one is known as Titan, the moon of Saturn, and it's the only moon in our solar system that has a substantial atmosphere. It actually has an atmosphere thicker than the Earth. So here's the surface, and there's this kind of thin haze. And the surprising thing, as I said, is something like 1.5 times as high atmospheric pressure on this moon. And it's mainly like 90% nitrogen, and the Earth's is something like 80% nitrogen. So it's actually quite similar in the main content, but it doesn't have oxygen. The rest of it are these poisonous gases, methane and things, ammonia. But the other thing that is somewhat Earth-like is the only other object in our solar system that has liquid on its surface. But it's not liquid water, it's liquid methane, combination of methane and ethane. We're not sure exactly. But we have had one lander from this Cassini mission, which landed on the surface. It wasn't a rover, so it couldn't move around. But it confirmed the presence of these lakes that they're called near the poles of Titan. So the only other object in our solar system that has liquid on its surface. Is there life? If so, it would be a very different kind of life than we have on Earth, because there's no oxygen. So that was kind of a quick tour of our solar system. Here it is all together, all to scale, the huge sun. So Mercury, Venus, Earth, Earth's moon, Mars, big Jupiter, Saturn, Uranus, Neptune. Here Pluto and its big moon Charon, and Eris. So Eris is the reason Pluto got declassified from a planet. It's an object in the outer part of our solar system that's probably a little bit bigger than Pluto, and so rather than calling it the 10th planet, and there are many other objects on the far reaches of our solar system, these small icy bodies, they were reclassified as dwarf planets. And there's something like a half dozen now, but then there are thousands more that are much smaller. And to be called a dwarf planet, you have to be spherical. The reason why Pluto is no longer considered a planet is because it no longer has, its orbit is filled with many other small objects, like Eris. So it hasn't cleared out its orbit, but it has enough mass to be spherical, so it's considered a dwarf planet.
Which planet is mostly water? Jupiter? No.
But so both Jupiter and Saturn are mainly hydrogen and helium, but the densities vary. So the density of Earth is something like 5.8 grams per cubic centimeter. The density of water, by definition, is 1 gram per cubic centimeter. So the density of Earth is something like 6 times the density of water. Venus and Mars are both rocky. They're pretty similar. Jupiter is something like 2 times. It's this big gas ball. So it's more dense than water. But Saturn, because of its size and composition, its density is actually less than that of water. So it's the only planet that would float if you could put it in a tub of water. And Uranus and Neptune are more dense. So Saturn is the one that has a density most similar to water, but it's mainly hydrogen and helium. But of course, there are many worlds beyond our own solar system, and the first, not proof because we knew this before, but the first direct measurement of it, it's kind of squashed here, was just a couple years ago. So 2017. So in our own solar system, we know the 8 major planets. We know half a dozen dwarf planets. We know thousands of comets, asteroids, and other things. Many dozens of moons orbiting the planets. But in 2017, we detected the very first object in our solar system that came beyond the solar system. So this object that actually came above our solar system's plane, down through, and on September 9th, 2017, it passed about the distance of Mercury from the Sun before being deflected around back in the other direction. And let's see, here's the Earth. And it crossed the Earth's orbit on October 7th, 2017. A couple days later, it was discovered. It was first imaged by an observatory on Maui. It's called Haleakala on Maui, called Pan-STARRS. And they took a picture of it on a couple different nights, and they saw how fast it was moving. If something is moving faster than about 40 kilometers per second, the sun can't hold it. So it's going too fast. It has more than the escape velocity. And this had something like 100 kilometers a second, much too fast. And so it was the sun's gravity was not enough to close its orbit, to keep it bound. And so it was realized that this was the first object, the first interstellar object detected directly in our solar system. And it was named Oumuamua, which is a Hawaiian word because it was discovered in Hawaii. It means a messenger from the distant past. So it had been traveling millions of years through interstellar space from its home stellar system, its home planetary system, was ejected by some violent event, and now millions of years later passed through our solar system. And people are trying to understand how many of these things are flooding interstellar space.
And what's the date?
It passed by the sun on September 9th, 2017, but it was not discovered, and so it plunged. So if this is a solar system, it came like this. It plunged down right near the orbit of Mercury, and then went up like that. And then as it was going up like this, people on Maui took a picture of it, and so that was right around October 14th.
And what is it, an asteroid or what?
It's asteroid-like. So it didn't have a tail, so it's not a comet, which was a surprise. So it was probably a rocky object, but it's so small and was moving so fast, we don't have any high resolution. We don't have any real pictures, just little dots of light.
Is it in an orbit?
What?
Is it in an orbit?
It is in a hyperbolic orbit, so there are different kinds of orbits. So in a gravitational field, I guess the simplest is a circular orbit, which is kind of like the Earth, although it's actually elliptical. So most things move in elliptical orbits around the sun. Comets have things that are almost parabolic, meaning that a parabola is an ellipse which stretches to infinity. So at infinite distance, it would turn around, kind of mathematically. This was more open than a parabolic orbit. It's hyperbolic. So its orbit was just a trajectory which flew by the sun, and then we detected it, and our observatory suddenly got all these requests to image this thing, to take spectra and try to figure out what it was. And so now it's far beyond the reach of any telescope, somewhere back out in interstellar space. We want to know how many of these things are actually in interstellar space. The predictions are that there are trillions of them, but we've only seen one so far. Yep.
Did it enter and leave the area at the same speed?
Yeah, pretty much. I mean, well, as it fell right by the sun, I guess it was at its highest velocity, kind of at the bottom of the potential well. So as it slung by, but because it's not bound to the sun, unlike the Earth and anything else we know in the solar system, it was moving too fast to have its speed changed by much. So yeah, it's pretty much the same. So that was the first interstellar object detected in our own solar system. But over the past decade, there's been a mission called the Kepler mission in orbit actually not around the Earth, around the sun, which stares at a certain area of the sky and measures the change of brightness of thousands of stars. And it's so sensitive that it can measure the tiny change in the brightness of a star as a planet around that star passes in front of it. And as a result of this Kepler mission, we now know of something like somewhere between 3,000 and 5,000 planets that go around other stars. And we've seen them pass in front of those stars many times, and so we can measure their orbits. There's this one particularly interesting system, which is a nearby small star called TRAPPIST-1, which has 7 planets going around. So 7 different objects have been seen to pass in front of it multiple times. So we know their orbits, we know basically their sizes because we know how much they change the amount of light. And the interesting thing is about 3 of them are actually in what's called the habitable zone. So that the Earth and Mars are essentially in the habitable zone around the sun. So it's a range of distance from the sun where liquid water can exist on the surface. So if Mars had a little bit more substantial atmosphere, maybe if the permafrost melted, it could keep liquid water on its surface, just like the Earth does. And so if at some distance from a star, if the temperature is right because of the amount of radiation, that's called the habitable zone. So life could exist. Liquid water could exist, so life as we know it could exist. Of course, it depends on many other things, like does the planet have an atmosphere? Is it big enough to have an atmosphere to maybe even have a magnetic field? But this is the first one that's been found to have multiple planets. So it was named TRAPPIST-1 because of it was actually first detected by this small telescope in Chile called the TRAPPIST telescope. But then it was followed up by this NASA telescope, the Kepler mission. And then it was a big news release a couple years ago. I was actually teaching a planetary science course in Victoria, which is where I was before Chile. And so it was a lot of fun to talk about this with the students. And as I said, multiple planets around this TRAPPIST star are in the habitable zone. So could almost be like the Hawaiian Islands. So seven planets going around TRAPPIST-1. So TRAPPIST-1e, so they're named TRAPPIST-1 A, B, C, D, E, F, G, maybe. And so TRAPPIST-E would be one that might have liquid water. And so people are making posters already about planet hopping for vacation on the TRAPPIST-1 system, kind of like Hawaii. Not all of them are habitable, just like not all the Hawaiian Islands. Okay, so just to kind of put this into perspective, the TRAPPIST system, the interesting thing about it, it's a red dwarf. It's a very small star compared to the Sun, only a little bit bigger than Jupiter. So its habitable zone wouldn't be like, the Earth is 93 million miles from the Sun. So around a tiny red star like TRAPPIST-1, it would be something like 6 to 10 million miles, much closer to the star. So to kind of put this in perspective, these are a number of different panels showing the relative sizes of things to scale. So we have Mercury, Mars, Venus, which is very similar to the Earth in size. Of course, Venus has a runaway greenhouse effect. It's something like 95% carbon dioxide. That's why the temperature is 800 degrees. It's not because it's so close to the Sun, but it has just this enormous greenhouse effect, the global warming gone crazy. Very similar to size in Earth. And then the next panel over shows Earth right here compared to the giant planets. So Earth, I guess this is Neptune, Uranus, Saturn, and Jupiter. So Earth to Jupiter. Then down here, this is Jupiter, the largest of our planets, much larger than Earth, compared to some stars. So this is a red dwarf star, like TRAPPIST-1, the one I was just showing that has these 7 planets, but it's actually called Wolf 359, named after some astronomer named Wolf. So Jupiter, a giant planet, compared to a very small star, a red dwarf, compared to our Sun. Jupiter's almost big enough to be a second star in our solar system. So the Sun compared to Sirius. So Sirius is the brightest star that we can see with our naked eye. It's in the constellation Canis Majoris, the big dog. The brightest star in the sky, but it's not super big. It just happens to be bright and close. And then here's Sirius, this brightest star in the sky, compared to a class of stars that we call red giants. So this is Pollux, one of the stars in the constellation Gemini, Arcturus and Aldebaran. Those are red giants. But red giants aren't the biggest types of stars. They're almost as big as something called blue supergiants. So down here is Aldebaran, this red giant, compared to something called a blue supergiant, which looks quite small. It's Rigel, because it's being compared now not to red giants, but red supergiants. So Rigel, blue supergiant, Antares, and Betelgeuse. You guys have heard of Betelgeuse, right? Yeah. So that's a red supergiant. And then here's several other more examples of red supergiants: Betelgeuse, Mu Cephei, VV, Canis Majoris. So this, again, how small Earth is compared to Jupiter, compared to our Sun, compared to Sirius, compared to red giants, compared to something like Betelgeuse and the red supergiants. Our Sun is above average, actually, in terms of numbers of stars, because there are many more small stars than there are big stars. But in terms of the actual size, it's tiny compared to the largest stars. Making up this slide here, I was kind of struck. Rigel is this bright blue star that you can see in the night sky. Betelgeuse is this bright red star, and they both happen to be in the same constellation. Okay, so can you see this? Orion, that's right. Orion, a beautiful winter constellation. You can see here this nice fence and the snow line lane, or maybe somewhere in New Hampshire or something. Let's just zoom in on that and change the contrast a little bit. So this star, this bright red star is Betelgeuse. It's the right shoulder, I guess, of Orion, the hunter. The left shoulder is another star called Bellatrix. This is Rigel. Depending how it's drawn, it's either the left knee or the left foot. I'm not sure what this one is. The right knee or right foot. I don't know the name. There's 3 stars of the belt, so the shoulders. This is the little head up here. The belt are Alnitak, Alnilam, and Mintaka, these 3 stars. And then the sword of Orion hangs down here. If we kind of zoom in on that, the middle part of the sword is not actually a star, but a nebula. It's called the Great Nebula in Orion. This is a picture taken with the Canada-France-Hawaii telescope, a wide-field, ground-based image, showing the main part of the Orion Nebula and some other associations. And then we kind of transition. This is the Hubble space image, kind of zoom in on the Orion Nebula. And so what is this? This is a bunch of mostly hydrogen and helium, again, gas, forming stars. It's a region where stars are being born. Hydrogen, helium, other light gases like that are the materials, the ingredients to make stars. And so the Orion Nebula is one of the most active star-forming areas in our local part of the galaxy. So our galaxy is not forming as stars as much as some others, and there are bigger regions far away from this. But this is something like 300 light years, so in cosmic terms, quite close, and it's forming many stars. And how we know that, we can zoom in further with the Hubble Space Telescope, and you see these little blobs here. They're called Bok globules, and they are dark. And this is in infrared imaging. You can see these dark lanes. Those are disks of material which are forming planetary systems around nascent stars, new stars that are being born out of the dense gas of the Orion Nebula. So yeah, we have planets, stars, galaxies in the universe. So our galaxy is still making stars like our sun. And then we zoom back to Orion. Orion is not the only place making stars. The Hubble Space Telescope has studied star-forming regions throughout our galaxy. This is kind of an iconic image taken by Hubble some years ago. These are these big gas plumes and pillars where the gas and dust has gotten really dense, where it's contracting to form stars, and so it's too dense to actually see through. And this is known as the pillar. It was just kind of a publicity name, the Pillars of Creation, because it's creating stars out of these out of this plumes of material. It's actually part of a larger structure called the Eagle Nebula. And once these stars contract out of this gas and dust that condenses and gets really thick because of gravity, the stars turn on. The density becomes high enough that hydrogen starts fusing into helium. So that's a nuclear reaction. That's nuclear fusion, releasing this enormous amount of energy. And so that's how stars work. That's how stars create radiation and energy, by nuclear fusion. And once that happens, then we get this enormous streams of material, radiation, solar wind, or stellar wind in this case, and they blow out all that gas. So this is a very young cluster of stars that's just turned on, born all together out of a very dense region of gas. A young cluster of stars just turned on. And in comparison, here's a very old cluster of stars. It's called a globular star cluster, NGC 6624. This is actually taken with the Gemini telescope. Zoom in, so you can actually see through it with the high resolution. But something like 500,000 stars in this very old cluster. It has no more gas from its birth. This is just a single filter, a single band, so it's monochromatic. But if you look at it in multiple colors, you can see, and with kind of very very sensitive color discrimination, you can see that the stars have different colors. And that's because once a star uses up all its hydrogen, it turns it all into helium. It builds up this core of solid helium in the center. And as the mass grows larger and larger, it goes through a different set of nuclear chain reactions in its center. Eventually, it can start fusing helium into other elements, carbon, nitrogen, oxygen, and it goes through something called stellar evolution. It's kind of the last gasps of life of a star. It tries to stay alive by burning more and more material, but as it does that, it gets just hotter and exhausts itself more quickly. And eventually, that star just runs out of material. It's not strong enough. It's not massive enough to keep fusing heavier elements, and so it just kind of dies. It kind of collapses on itself into something. If it's the size of the sun, it's something called a white dwarf. And it blows out its outer atmosphere. And so the last stages, kind of the death throes of a typical star like our sun, would be something like this. It's called the Ring Nebula, planetary nebula, where we're left with this burning cinder, a white dwarf in the center, and this beautiful atmosphere of the star that's been blown off. And there are many varieties of these planetary nebulae. And here's just the same exact thing. But something different happened in its last stages to create this structure. That's the same dead star at the center, this glowing white ember called a white dwarf. It no longer undergoes nuclear fusion. It's just glowing hot, and its atmosphere has been blown off. And can anyone guess what the name of this nebula is? What does it look like? What is it?
Snail?
Snail? Crab? No, not crab. Ghost, hello. What's that? It's called the Cat's Eye Nebula. Cat's Eye Nebula. I don't know. I'm not sure if it looks like a cat's eye. How about this one? This is the same thing. This is a different kind of planet. What? Did somebody just say? The butterfly? Yeah, so this is a butterfly nebula. It's also a dead star with a dead star somewhere in the center. It's blown off its atmosphere. It's probably a binary star, which is why it has this kind of bimodal structure. Not all stars die like that. Some die much more massive stars die much more violent deaths as supernovae. And this is the remnant, a supernova remnant. It's actually the remnant of a supernova that exploded in our galaxy that was viewed by the Chinese astronomers and actually Native Americans in the desert Southwest in the year 1054. They recorded the explosion on these pictographs and cave wall or cliff walls. So the Crab Nebula. So we know exactly when this one exploded. Just under 1,000 years ago, the Crab Nebula. It doesn't look too much like a crab. Okay, so just coming back to our galaxy, I just want to emphasize that everything I've talked about so far has been in our own Milky Way galaxy. This is an artist's drawing of something like the Milky Way, the bulge in the center, the disk, the spiral arms. I talked about a big old star cluster. Those are globular clusters that live out in the halo of our galaxy. And the sun is something like, a little more than halfway out in one of the spiral arms in our Milky Way. And again, our Milky Way is one of 40 or 50 galaxies in something called the local group. And the biggest galaxy in our local group is this one. It's the Andromeda Galaxy. It's something like, 2 million light years away. It has a couple satellite galaxies and actually lots of other ones at larger distances. It's about twice as big as our galaxy, the Andromeda Galaxy. It's also a spiral, but a more tightly wound spiral than ours. And there's a great variety. Anyone want to guess?
Snail.
Yeah, kind of. It's actually called the Rose Galaxy, right? It's kind of a spiral that's been disturbed. Okay, how about this one?
Needle. Tadpole.
Good, yeah. You said the Tadpole.
Okay.
Oh, okay, that's right. Yeah, this is one I worked on, actually, one of the first images with the advanced camera for surveys. I spent 5 years in Baltimore working at Space Telescope, so I did this image. The Tadpole, I was actually advocating for something, it actually doesn't look too much like a tadpole, because a tadpole doesn't have like a mouth. It looks exactly like a gulper eel, which is this deep sea ultra, but I was not able to convince the principal investigator to go with that name. So this is like a spiral galaxy that has torn apart some satellite. That's kind of like that comet that impacted Jupiter and got torn apart. Some galaxy got ripped apart by the gravitational field of this larger spiral to create this tail that comes out the back. This is a very different kind of galaxy. This is the giant elliptical galaxy M87. It's at the center of a cluster of galaxies called the Virgo cluster, which is about 55 million light years away. And it may be the biggest galaxy within about 100 million light years of the Earth. And it doesn't have all that structure, that spiral structure. It's very massive, and this thing that looks like a tail here is not a tail like I showed before. It's actually a jet of very high energy particles streaming out from the center. And this is the galaxy that you may have seen this image a couple months ago. It's the M87 Star is the name of the black hole at the center of this giant galaxy M87. And it is sitting there accreting, sucking in all this material. And these enormous magnetic fields cause these high energy particles to stream out in a high energy jet that you saw on the previous figure. And so it's been known for decades that the only explanation for the motions and the energy that we see in such a tiny region of the center of this galaxy, the only possible explanation we know of is a black hole. But this is the first time that it has been imaged directly, not with optical telescopes, but by an array of radio telescopes, the actual shadow of that black hole. So the data, the pictures were taken, the data which were combined later into a picture were taken just over a year ago. It took them about a year of analyzing the data to be sure that they had done it correctly and had actually seen this shadow of the black hole, the first time it's ever been taken. And how do we know that's the signature of a black hole? Because it's exactly what is predicted by Einstein's general relativity, which governs the way black holes work. And I'll come back to that at the end. It's exactly what we believe, kind of mathematically, the structure of a black hole should be. And then there are other galaxies. This is called Centaurus A. It's a giant radio galaxy in the constellation Centaurus in the southern sky. It has an even bigger jet of material from a central black hole. And it's very common. Just about all giant galaxies have evidence of massive black holes in their center, including the Milky Way, although much smaller than this. And big galaxies tend to live in clusters. I said M87 is the central galaxy in the Virgo cluster. This is a much bigger cluster of galaxies imaged with the Hubble Space Telescope. It's called Abell 1689, which is called that because it's the 1,689th cluster found by a guy named George Abell in the 50s. But now we have these high-resolution images with the Hubble Space Telescope, and we see the enormous amount of material and mass and gravitational lensing, which is the bending of background light into these arcs. So galaxies live in groups and clusters, and those clusters cluster together in superclusters. And on larger and larger scales, we see structure in the distribution and in the locations of galaxies. And this is a map kind of looking out in one direction in the sky, a big swath of sky. As you go further away, of course, an area, this size becomes larger and larger as you get further away because of the opening angle of the wedge. And so in two different directions in the sky, like that direction, you can map out how far away galaxies are. And this thing right here is called the Great Wall. It's a bunch of clusters that are linked together into a large structure called the Great Wall. And there are other structures, and this is very, very low resolution. If we could map it more perfectly, we would see how the galaxies are really distributed in this web structure throughout the universe. And here it's showing the distance. So this is 0.5 billion light years, 1 billion light years, 1.5 billion light years. So that's the distance of these galaxies that map out this structure in the cosmic web. I said at the beginning that the Milky Way was something like 14 billion the universe is something like 14 billion years old. So this is 1.5 billion. So that's 1/10 of the distance to the furthest things in the universe. And in fact, we can measure galaxies pretty easy out to 1.5 billion light years, and even further, out to almost 10 billion light years. And we can actually detect light from a time in the universe reaching us from distances before galaxies formed, before stars turned on. And we don't do that with optical telescopes, the images I've shown you so far, because that light has been redshifted. So as the universe expands, the light gets stretched out in longer and longer wavelengths. This very high energy blue light gets stretched to very long wavelengths, radio wavelengths. And so we cannot see the most distant things before the formation of stars and planets, both stars and galaxies with optical telescopes, we need arrays of radio telescopes. And when we do that and point to the distant sky, we're able to measure fluctuations in the intensity of the background light, the background radiation. So this is an all-sky image of the cosmic microwave background. So there's this radiation that just floods the universe from all directions. And it comes from a time before galaxies formed, before stars turned on. That means it's the primordial radiation, the primordial energy from the formation of the universe, the Big Bang. And by zooming in on it, you can measure the structure, the fluctuations in this radiation. And that corresponds to the density of the material at different parts in the early universe before the stars turned on. And the size of these fluctuations actually tell us an enormous amount about the history of the universe. Because the rules that govern the evolution of the universe, and evolution just means unfolding, right? It's a Latin word or Greek word, it means unfolding, how things have unfolded throughout the history. So there's biological evolution describing the history of life, or cosmic evolution, the history of the universe. But by measuring these fossil lights from 13.5 billion years ago, and applying some very simple rules figured out by this guy, we're able to know the age and the size of the universe. So, who is this guy? Einstein. Right. So Einstein is famous for the special and general theory of relativity. In 1905, he published his special theory of relativity. It's all about the way objects move and the way light interacts with objects. And one very simple consequence of his special theory of relativity was this: E equals mc squared. This was a necessary ingredient for his theory. It's something that kind of came out of his theory as he was trying to understand and explain the motion of light in different reference frames. As things, nothing can move faster than the speed of light. That's known. But that's strange. That means if you're on a train that's moving at 60 miles an hour and you shine a beam of light in that direction, it seems like it should be going the speed of light plus 60 miles an hour. But the paradox is that anybody in any reference frame always measures the same speed of light, even if it's shined by somebody moving at high velocity. And that was completely impossible to understand by Newtonian physics. And he spent years coming up with his special theory of relativity to explain the way light interacts with different observers in different reference frames. And this was a consequence, the conversion of mass into energy. And this factor, c, as I said, 186,000 miles per second, or 300,000 kilometers per second, is a big number. And if you square it, it's even much bigger. And so a little bit of mass creates a huge amount of energy. And that's how stars burn. That's how the sun creates so much light from converting its little bits of hydrogen into helium by nuclear fusion. It's also the same way that nuclear bombs generate such enormous amount of energy by tapping into this kind of energy source of the stars. So that was a necessary consequence of special relativity. But that wasn't good enough because it didn't explain the way gravity worked. And so he spent another 10 years, and in 2015 he published his general theory of relativity. And this looks really scary, but it involves the combination of light and gravity. And as a consequence, you can actually explain the whole evolution of the universe. And this is an equation that comes from Einstein's general relativity, having to do with the acceleration, how fast the universe is expanding. And you don't have to worry about all these other constant terms, except that g means gravity. And this negative sign means slowing down, subtracting. And so how fast something expands, how the expansion is slowed down by gravity. So the the Big Bang that happened 13.8 billion years ago should be slowing down because of all the gravity of the universe, all the material in it kind of counteracting that explosion. Except that there's this other term that comes up in general relativity, which is called the cosmological constant, or now we call it dark energy. This thing that looks like a little teepee is the Greek letter, capital letter lambda. And it's this strange energy that permeates the universe and tries to make things speed up. And the whole evolution, the whole expansion history of the universe is kind of an interplay of gravity trying to slow things down and the cosmological constant, or dark energy, trying to speed things up. Mostly around the Earth, the only thing we care about is gravity. The cosmological constant, dark energy, that doesn't bother us. And so we know general relativity works because it can perfectly explain how gravity warps space and explains the orbits of satellites and the light travel times from distant objects. It works to enormously high precision. It's been verified over and over again for over 100 years. And it explains not only the motions of satellites around the Earth. If general relativity were not correct, the whole GPS system would not work, because the GPS, which tells us our locations on Earth, has to take into account equations, simplified versions of equations that Einstein came up with in 1915. But it also explains much more esoteric phenomena like this gravitational lensing, and this is something called the Einstein Cross. In 1936, Einstein wrote a paper predicting that light can be bent into multiple images or even rings by other massive objects. And it was really verified in the 1980s. This was one of the first examples of a gravitationally lensed system. So it's actually one object in a distant background being, its light being bent into 4 different images by an intervening galaxy. And it's cross-shaped. It's known as an Einstein Cross. You can also get Einstein rings. And so all of these things confirm the general relativity that was published by Einstein in 1915. But it took a different kind of person to explain the history, the formation, to use Einstein's equations in a new way. This man that Albert Einstein is talking with is Georges Lemaitre. He was a Belgian Catholic priest. In the 1920s, he was doing his PhD in physics at MIT. And he used Einstein's equations, published about 10 years ago, to try to understand the history of the universe. He applied them. He showed that general relativity can explain the motion over time. You can extrapolate it backwards from our current universe to what we observe today backwards. And it would predict that all matter would come together. He didn't know, because distances were not well determined then, he didn't know how long it would be, but he knew it was billions of years. And he knew that some billions of years ago, all the matter must have been in a tiny sphere of high-energy material, high-energy plasma. And he named it the primordial fireball, right? So Einstein, when he first heard about this, he was initially very skeptical. You had a Catholic priest talking about the formation of the universe and this cosmic fireball, this primordial fireball, kind of the let there be light, and using his equations. And so he was quite skeptical that it sounded too much like religion to him. But he attended a talk around 1930 by Lemaitre about this model, this primordial fireball. And when he understood the equations, when he understood how his general theory of relativity was being applied so carefully and so strictly to explain the evolution of the universe, his comments after hearing it and understanding it was, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." And Einstein became a great advocate and fan of this model, originally theorized by this Belgian priest. As I said, Lemaitre himself called it the primordial fireball. There were people who kind of criticized it, and they named it, mockingly they called it the Big Bang, right, instead of the primordial fireball. And that's the name that stuck. So the Big Bang model, right? And we all, essentially all astronomers today realize that that's the way that the universe has changed, because we can observe it directly now. as I said, general relativity is not just about gravity. There's something, this more mysterious extra term with a plus sign instead of minus sign. Einstein saw no evidence for it back in the 1915. Lemaitre, nobody really saw evidence for it until 1998. Well, starting in the 80s, there was some hint that this anti-gravity, the plus term instead of the minus term, existed. It's called the cosmological constant, or the more general term is dark energy. And now we know that, contrary to expectations, the expansion of the universe is not slowing down because of gravity. It's actually speeding up because of the cosmological constant. So as the universe expands, it's accelerating because of this dark energy that permeates the universe. We don't know what it is. We know that it's explained by general relativity. We don't know how to tap into it, but the US Department of Energy suddenly became interested in astronomy after this was realized that the universe is permeated by this dark energy, this infinite source of energy that can only be seen over enormous scales. So again, all this is explained by, predicted essentially by the equations of general relativity. They explain what we observe in the universe. And this comes back to another quote by Einstein. He said that the most incomprehensible thing about the universe is that it's comprehensible. So why would that be? Why should we be able to understand the way the universe works? It could just be a big mystery beyond our reckoning. But using the essentially equations that he worked out 100 years ago and applying them to modern observations, we can really understand the way the universe works. And we see it not only from the Earth, so just to kind of conclude here, now that we've sent out, as I showed, the Cassini mission has orbited Saturn for 10 years, another one, Jupiter. We've sent the New Horizons probe has now flown by Pluto. I had an image, actually, if anyone wants to see, I took it out, a close-up of Pluto. But some of the first space missions that have gone out of our solar system were launched in the early 70s, the Voyager 1 and Voyager 2. They went by the major planet, Jupiter, Saturn. Voyager 2 went by Uranus and Neptune as well. And after 35, 40 years, they actually exited our solar system. The limits of the solar wind is considered the limits of our solar system. It's out beyond the orbit of Pluto. And in the late 90s, before Voyager 1 reached that limit, as it was exiting our solar system, it turned its camera around just to make one last photo, a parting image as it was departing our solar system. And this is the image. Can anybody see anything interesting?
It's a white dot.
The white dot, right. And it just it pointed towards the Earth as it was exiting the solar system after 35 years. And now it's been like 45 years. And it just so happens that the sun, because it's so far away, the sun is very close to the Earth, and there was this streak of light from the sun in essentially the glare on the camera that just happened to go right through the Earth. And Carl Sagan has a book that talks about this event, the Voyager missions, in this last image. And he has one paragraph, or a couple paragraphs, about this final image of the Voyager 1 mission as it took this image of the Earth exiting the solar system. And let me just read it. Let me get one sip of water for you. So Carl Sagan in his book, Pale Blue Dot, A Vision of Human Future in Space, describing this image of the Earth, he says, "Consider again that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam, the only home we've ever known. So it's meant to try to put things into perspective. You can look at this in kind of a fatalistic way, maybe the philosopher in Dostoevsky's novel, in a cynical way that nothing we do matters. We're just on this tiny dot. But you can look at it in a different way, that we're all sharing this one tiny dot. All of our disagreements and all of our wars and battles and human conceits have all taken place in this tiny dot. And there's so much more common interest than we have, than than separates us. And we really do need to preserve and treasure this one dot that we know that harbors life in the universe. So it can be looked at in a more hopeful way. And so there's again a blow up of that one dot. That's all I have. Sorry, I went on a little long.
Comment and a question, Dr. Blakeslee. The space elevator has been proposed for our islands about a year ago, but it doesn't look like we're going to get it now because of activism and things like that. But is there any prospect for that in the future?
Yeah, I mean, it's not something I know a whole lot about space travel, but in the future, sure. I don't think it's something that we'll see in the next decade or two. Yeah. To reach like the orbit, right, from the Hawaiian Islands.
Yeah, 22,000 miles.
Yeah. I guess to geocentric orbit. Yeah. I don't know too much about it. I think it's technically very challenging, and so if there were an economic incentive, I'm sure entrepreneurs would do it.
Chemical rockets are expensive, and
yeah.
all those trips up there to the Hubble telescope and the International Space Station. So
yeah.
it's,
So
it's,
I don't know.
it's technology. I wish we had it.
Yeah, it's the kind of thing that if Elon Musk suddenly became interested in it, we may have it, but we need somebody with billions of dollars to take an interest. Yeah. Yes.
Do you have a favorite personal telescope
A favorite personal telescope
that you like as a hobby?
as a hobby? Well, I had one as a kid, a long time ago. The one that I probably used the most in my own research, my own science, has been the Hubble Space Telescope. I did my PhD thesis using a small 2-meter telescope on Kitt Peak in Arizona. And so I spent many nights there on an isolated mountain in Arizona. But from 2000 to 2005, I was working with the Advanced Camera for Surveys mission as part of the Hubble Space Telescope. And so, although I said it's a very expensive solution to correcting the turbulence of our atmosphere, it's such a nice one, getting above all the clouds and the turbulence. So it's a lot easier to work with data from Hubble than many other telescopes.
You said that the universe is expanding, but what is it expanding into?
Yeah, so it's a good question. You think of the universe as all of space. So there's a kind of a 2-dimensional or 2 to 3-dimensional analog, right? So you imagine a balloon, right? And you take a balloon and maybe you paint the whole balloon a certain color. And then you blow into that balloon, and the balloon gets larger. This energy is being injected from your lungs. And all those little flecks of paint suddenly start moving further and further apart, all these little dots, or maybe they're ants on that balloon. And as the energy is injected by your lungs, the surface of that balloon expands. And you think of, and so the ants on that balloon or the flecks of paint get further and further apart as the surface of that balloon expands. And you can scale that up by 1 dimension. You imagine the universe as being a 3-dimensional surface of some 4-dimensional larger reality. And so as you can see that as the balloon expands, the whole surface is just growing, and the distance, the space between the objects on that balloon is getting larger. But from somebody living on the surface of that balloon, they wouldn't see, they are two-dimensional objects, and so their whole space is just growing, but it's not really expanding into anything. And it's the same thing with the universe, that space itself is expanding. It's kind of a bubble of reality. That's the physical explanation, right? So you can work out, not exactly general relativity, you have to go a little bit beyond it to really understand anything beyond the Big Bang. But there's not an actual expansion of the universe into anything. It's just an expansion of space itself. So all space is growing, but it's closed. You know, just like the surface of that balloon.
Yeah, but when you compare it to the balloon, it sounds like someday, like,
It could pop.
yeah, it could pop.
Yeah, hopefully we won't be here when that happens. Or yeah, and in fact, the dark energy causes the expansion to go faster and faster. Yeah, so we don't know. We can't forecast beyond, you know, so many billions of years what will happen.
So
Yes.
a picture of the black hole. I mean, how old? I mean, when it was taken, how long did it take for that, you know, for us to get it?
So I actually have a maybe next to the Pluto. Okay, so the way the black hole image was taken was by radio telescope scattered across the surface of the Earth. So as the benefits of having larger telescopes is higher resolution. So you can distinguish things, separations on the sky, better as you have a larger aperture. And that's true with optical telescopes, with lenses and mirrors. It's the same thing for these radio telescopes that were used to make the image of the black hole. They were spread all across the Earth, and they took data simultaneously. And this was done in the data that were taken were in April 2017, so just over a year ago. And then they spent a year, basically almost a year, combining the data from all these different sites, making sure that they understood the light travel times for every point in that image. So it's a whole lot of image processing that is required from these 7 or 8 antennae spread across the Earth to get that image. So if the question is, how long did it take between when they took the data and when we saw the image? Something roughly a year.
No, I
But
mean,
how long did it take for the light to reach us from the black hole? So as I said, M87 is the biggest galaxy in the center of the Virgo cluster, and this black hole that they image is at the center of that galaxy. And we know that the distance of that galaxy is 55 million light years. So the light travel time, that image took 55 million years to reach us from that galaxy. So in a sense, we're seeing it as it was 55 million years ago. But that's kind of a small amount of time on cosmic scales of billions of years.
So we have some stickers, all kinds of nice things, so please take a moment to check on them.
And that there are 10 or 12 pamphlets on careers in astronomy. So
Right.
not just astronomers like me, but lots of IT people, technicians, engineers. If you're interested, especially younger people, take a pamphlet on careers in astronomy. And there are great opportunities here in the Hawaiian Islands.